Classical foundations. The physics of Galileo and Newton. Before Einstein, the concepts of space and time were considered absolute and unchanging. Imagine space as a vast, infinite, and static stage. This stage is three-dimensional, with its length, width, and height, and it exists regardless of whether any actors are upon it. This was the view of absolute space, a fixed background against which the cosmos played out. Similarly, time was thought to be an absolute river, flowing at a constant, universal rate from the past through the present and into the future. Every clock in the universe, no matter where it was or how it was moving, would tick in perfect synchrony with every other clock. This absolute time was the master clock of the cosmos. This idea of a fixed stage and a universal clock is deeply intuitive. It feels right, and it formed the bedrock of Newtonian physics. Now, let us introduce the actors onto this stage. The first great insight came from Galileo, who formulated a crucial principle of relativity. He asked us to imagine being in the windowless belly of a large ship. If that ship is moving at a constant, smooth velocity across a perfectly calm sea, can you perform any experiment, dropping a ball, watching fish swim in a tank, observing the swing of a pendulum that would tell you whether the ship was moving or stationary? Galileo's profound answer was no. The laws of mechanics, the laws governing motion, operate identically inside any system that is moving at a constant velocity. There is no experiment you can conduct to detect a state of uniform motion. You can only detect acceleration, a change in speed or direction. This is the principle of inertial frames. The physics on a smoothly cruising train, airplane, or planet is identical to the physics in a stationary room. It was Isaac Newton who, building upon the work of Galileo and others, synthesized these ideas into a comprehensive mathematical framework. In his monumental work, the Philosophiae Naturalis Principia Mathematica, published in 1687, he laid down his three laws of motion. The first law, the law of inertia, formalizes Galileo's insight. An object at rest will remain at rest, and an object in motion will continue moving in a straight line at a constant speed, unless acted upon by an external force. This is not a statement of everyday experience, because on Earth, forces like friction and air resistance always act to slow things down. But in the vacuum of space, this law reveals the true nature of motion. His second law gives us the famous equation, force equals mass times acceleration, or F equals ma. It quantifies how an object will respond when a force is applied. But it was his third law that provided a deep symmetry. For every action, there is an equal and opposite reaction. When you push against a wall, the wall pushes back against you with equal force. Yet, Newton's most breathtaking contribution was his law of universal gravitation. This was a truly radical idea. He proposed that every single particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This is often called the inverse square law. In simpler terms, the gravitational pull between two objects gets stronger if their masses increase, and it gets weaker, specifically 4 times weaker if the distance between them doubles. Think of the Sun and the Earth. The Sun, with its enormous mass, creates a gravitational field that reaches across 93 million miles of empty space and pulls on our planet. This pull, constantly acting at a right angle to the Earth's forward motion, bends its path into a near-circular orbit. It is the same force that causes an apple to fall from a tree. Newton had unified the heavens and the Earth under one simple, elegant law. The same force governing the Moon's orbit around the Earth was also governing the fall of everyday objects. This framework was phenomenally successful. It allowed astronomers to predict the motion of planets and comets with stunning accuracy. It explained the tides as a gravitational interaction between the Earth, Moon, and Sunday. For over 2 centuries, Newtonian physics was synonymous with the ultimate description of reality. It was a clockwork universe, deterministic and predictable. If you knew the position and velocity of every particle in the universe at one moment, you could, in principle, calculate all future and past states. The universe was a magnificent, predictable machine. But let that concept settle in for a moment. In this Newtonian world, gravity was a mysterious, instantaneous force acting at a distance. How does the sun, across vast emptiness, reach out and pull the Earth? Newton himself was deeply troubled by this, calling the idea of action at a distance so great an absurdity. Yet, the mathematics worked flawlessly for describing the motions of planets and projectiles. It was a powerful and effective description, but it left a profound how unanswered. The stage was set, the actors knew their lines, but the mechanism behind one of the most fundamental forces remained a beautiful mystery. As you drift closer to sleep, picture this grand, classical universe, a vast, fixed stage of space, a relentless, universal flow of time, objects moving predictably according to Newton's elegant laws, pulled by an invisible, instantaneous force of gravity. It is a complete and comforting picture. But as the 19th century drew to a close, a few small, seemingly insignificant cracks began to appear in this solid foundation. The first of these cracks involved the nature of light, and it would set the stage for a young patent clerk to rewrite the rules of the cosmos. This classical picture was elegant and powerful. But as the 19th century drew to a close, a few small cracks began to appear in this solid foundation, starting with the behavior of light, which we will explore in our next lesson. The crisis in physics, the Michelson-Morley experiment. As you continue to relax, allowing the tensions of the day to fade away, we turn our attention to the late 19th century. The world of physics, built upon the formidable foundations of Newton, seemed complete. The great physicist Lord Kelvin is famously quoted as saying that there was nothing new to be discovered in physics, and that all that remained were more and more precise measurements. It was an age of confidence. But in science, as in life, it is often in moments of supreme confidence that the most profound questions emerge. And the question that would unravel the classical world was a deceptively simple one. What is the medium through which light travels? To understand this question, we must think about waves. A sound wave is a vibration that travels through the air. Ripples on a pond are disturbances that travel through water. Every wave known to science needed a medium, a substance to oscillate. So, what was the medium for light? Light, as James Clerk Maxwell had brilliantly shown, was an electromagnetic wave. It was natural, then, for physicists to assume that light, too, must be traveling through some kind of substance. This hypothetical, invisible, and frictionless substance was given a name: the luminiferous ether. It was imagined as an all-pervading, static fluid that filled all of space, even the vacuum, providing the necessary medium for light waves to ripple through. It was the stage upon which the drama of light played out. The ether had to have some very peculiar properties. It had to be incredibly rigid to allow light to travel at its tremendous speed of 300 million meters per second, yet it had to be completely frictionless, offering no resistance to planets and stars moving freely through it. It was a paradoxical concept, but it was a necessary one for the classical worldview. If the ether was real and static, then the Earth, as it orbits the Sun at a speed of about 30 kilometers per second, must be moving through this ether sea. Just as you feel a wind on your face when you cycle, even on a still day, the Earth should be experiencing an aether wind as it plows through this cosmic medium. This is where our story focuses on two American scientists, Albert A. Michelson and Edward W. Morley. In 1887, in a laboratory in Cleveland, Ohio, they designed and conducted what is perhaps the most famous null result in the history of science. Their goal was straightforward: to detect the ether wind, to measure the Earth's motion through this fundamental medium. Their instrument, an exquisitely sensitive device of Michelson's own invention called an interferometer, was capable of measuring fantastically small differences in the speed of light. Let us picture how this worked. The interferometer used a beam of light which was split into two perpendicular paths by a half-silvered mirror. One beam travelled directly along the direction of the Earth's supposed motion through the ether. Let us call this the parallel beam. The other beam travelled at a right angle to this motion, the perpendicular beam. The two beams were then reflected back by mirrors and recombined. If an ether wind was blowing, it should have affected the two beams differently. Think of two swimmers in a river, one swimming directly upstream and back, and the other swimming the same distance across the river and back. The swimmer going across the current will always win the race. Similarly, the beam of light fighting against and then surfing with the ether wind should take a slightly different time to complete its journey than the beam travelling across the wind. Michelson and Morley calculated that this should create a tiny shift in the interference pattern, a set of light and dark fringes, when the two beams reunited. Their apparatus was so sensitive that it was mounted on a massive stone slab, floating in a pool of mercury to isolate it from vibrations, and they could rotate it to test for the ether wind from different directions. They performed the experiment at different times of the day and year to account for the Earth's changing velocity. The scientific world waited with bated breath for the result that would confirm the existence of the ether. The result was a profound silence. There was no shift, no change in the interference fringes, no detectable ether wind whatsoever. The experiment found nothing. The speed of light, measured along the Earth's direction of motion and perpendicular to it, was exactly the same. The parallel beam and the perpendicular beam took precisely the same time to complete their journeys. It was as if our two swimmers, one battling the current and one crossing it, returned at the exact same instant, as if the river itself had no flow at all. The implications of this null result were staggering. It was a crisis. The Michelson-Morley experiment had confidently set out to measure the properties of the ether, and instead it found no evidence that the ether existed at all. This was deeply troubling. How could light be a wave if it had no medium to wave in? How could the Earth be moving at 30 kilometers per second through a stationary ether, yet this motion be completely undetectable? Physicists were confronted with a paradox that struck at the very heart of their understanding of space and motion. In the years that followed, many attempted to patch the leaking ship of classical physics. The most notable attempt was the Lorentz-Fitzgerald contraction, a proposal that objects physically shrink in the direction of their motion through the ether by just the right amount to exactly cancel out the effect Michelson and Morley were looking for. It was an ingenious, if somewhat desperate, solution. It saved the phenomena, but it felt ad hoc, like a convenient fiction invented solely to explain away a failure. The ether, this mysterious, undetectable substance, was beginning to look less like a scientific concept and more like a metaphysical ghost. So, as the 20th century dawned, physics found itself at a crossroads. Its most fundamental assumptions about space and the nature of light had been called into question by a brilliant experiment that found nothing. The elegant, mechanical universe of Newton now had a deep and persistent crack running through its foundation. The ether, the supposed stage for the cosmos, had vanished into thin air, leaving behind a vacuum of understanding and a profound, unsettling question. If there is no ether, what is light moving through? The failure to find the ether left physics with a deep and troubling puzzle. For nearly 2 decades, this paradox lingered. It was a young patent clerk, Albert Einstein, who would boldly resolve this crisis not by inventing a new substance or a convenient contraction, but by re-examining our most basic, unshakable assumptions about space and time themselves. Einstein's postulates, the foundation of special relativity. As you drift deeper into a state of relaxation, let us leave behind the perplexing null result of the Michelson-Morley experiment. For nearly 2 decades, it remained an unsolved puzzle, a ghost in the machine of classical physics. Some of the greatest minds of the era tried to contort existing theories to explain it, but the solutions felt forced, like trying to fit a key into the wrong lock. The year is 1905. In Bern, Switzerland, a 26-year-old patent clerk, unburdened by the academic traditions of the time, is about to perform a feat of pure intellectual clarity. His name is Albert Einstein, and in his paper, On the Electrodynamics of Moving Bodies, he would not try to patch the old system. Instead, he would lay an entirely new foundation with two simple, yet profoundly radical principles. Einstein began not with complex mathematics, but with a thought experiment. He asked us to imagine ourselves once again, not on a ship, but holding a mirror. If you were to run forward at nearly the speed of light, what would you see in the mirror? According to classical physics, the light from your face would struggle to catch up to the mirror you are carrying, and your reflection would vanish. This seemed absurd to Einstein. Why should the laws of optics be different from the laws of mechanics? This line of thinking led him to his first postulate, which is a grand extension of Galileo's principle. It is called the principle of relativity. It states that the laws of physics are exactly the same for all observers in uniform motion relative to one another. Let that idea settle in. This means that whether you are sitting perfectly still in this room, or cruising smoothly on a high-speed jetliner, or even orbiting the Earth in the International Space Station, every single experiment you perform, be it mechanical, electrical, or optical, will yield the exact same results. There is no privileged state of rest. There is no absolute motion. You can only measure your velocity relative to something else. There is no way to tell if it is you who are moving, or the world around you. This postulate elevates a principle of mechanics to a fundamental law of the entire universe. It declares a profound democracy of all inertial frames of reference. Now, this first postulate, on its own, was revolutionary, but it did not directly solve the crisis of the ether. For that, Einstein needed a second, even more daring postulate. He looked at the evidence from Maxwell's equations, which perfectly described light as an electromagnetic wave, and at the stubborn null result of Michelson and Morley, and he made a breathtaking leap. He proposed his second postulate, the constancy of the speed of light. This states that the speed of light in a vacuum, always denoted by the letter times c*, is always the same for all observers, regardless of the motion of the light source or the observer. It is a universal constant, approximately 300 million meters per second. This is the concept that shatters our classical intuition. Let us paint a picture to make this clear. Imagine a spacecraft traveling at half the speed of light, away from Earth. It turns on its headlights. From our classical, Newtonian perspective, we on Earth should measure the light from those headlights as traveling at the speed of light, plus half the speed of light, 1.5 times c*. Conversely, an observer on the spacecraft might think the light from our sun is reaching them at the speed of light, minus half the speed of light. This is how velocities normally add. But Einstein's second postulate says this is wrong. Both we on Earth and the astronaut on the spacecraft will measure the very same beam of light from those headlights as moving at exactly 300 million meters per second. Not a fraction more, not a fraction less. If you are still awake, try to feel the strangeness of this. It defies all everyday experience. If you throw a ball forward from a moving train, its speed, relative to the ground, is the speed of the train plus the speed of your throw. But if you switch on a flashlight on that same train, the light does not get a boost. It simply travels at times c*, forever and always, for you on the train, for someone standing on the platform, and for an alien in a distant galaxy watching the entire event. The speed of light is the ultimate speed limit, and it is immutable. This second postulate was the key that unlocked the puzzle of the ether. If the speed of light is always the same for every observer, then the very concept of a stationary ether medium becomes unnecessary. In fact, it becomes meaningless. The ether was a hypothetical substance whose sole purpose was to be a universal rest frame, a benchmark against which absolute motion could be measured. But if the speed of light itself is the benchmark, and it is the same for everyone, then there is nothing to measure against. The ether, as a concept, simply evaporates. Einstein resolved the crisis not by discovering what the ether was, but by showing, with impeccable logic, that we had no need for that hypothesis. Where other physicists clung to the old stage, Einstein realized the stage itself was the problem. He discarded it. In doing so, he unified the disparate principles of mechanics and electromagnetism into a single, coherent theory. He took the relativity of Galileo and extended it to the entire world of physics, and he took the constancy of times, c times from Maxwell's equations, and elevated it to a fundamental principle of nature. These two postulates are the bedrock. They are the firm ground upon which the entire, extraordinary edifice of special relativity is built. They are simple to state, but their consequences are anything but simple. They force us to reconsider the very fabric of reality. Accepting these two postulates leads to astonishing, yet inescapable, consequences. The first of these is a direct result of the constant speed of light, and it challenges one of our most basic assumptions about reality, that we all share a common, universal present, the relativity of simultaneity. As you rest, your mind open and receptive, we now venture into the first and perhaps most profound consequence of Einstein's two postulates. It is a concept that challenges an assumption so deep within us that we rarely even think to question it, the idea of now. We all operate under the belief that if two events happen at the same time, they are simultaneous for everyone, everywhere. It feels like a universal truth. But Einstein's theory reveals this to be an illusion, a consequence of our experience with slow speeds. The first brick to fall from the edifice of absolute time and space is the relativity of simultaneity. To understand this, we must engage in a thought experiment, a kind of logical daydream that was one of Einstein's favorite tools. Picture a long, straight railway embankment on a quiet, clear day. Standing on this embankment is an observer. Let us call her Anna. She is positioned exactly halfway between two identical trees. Now, imagine a very long train traveling along the tracks at an immense, constant speed, a significant fraction of the speed of light. Inside this train, seated in the exact center of one of the carriages, is another observer. Let us call him Ben. His position, relative to the train, is fixed. Now, let us introduce the event. At the precise moment that Ben's center of the train is directly opposite Anna's position on the embankment, two bolts of lightning strike the railway line. Crucially, these bolts strike the two trees, one in front of the train and one behind it. And here is the key condition. From Anna's perspective on the embankment, the two bolts strike at exactly the same instant. The light pulses from each lightning strike begin their journey toward her at the same moment. Since she is standing precisely halfway between the two trees, and because light, according to Einstein's second postulate, always travels at the same speed, c*, regardless of its source, these two light pulses will arrive at her eyes at the very same time. She sees a single, simultaneous flash from both directions. She concludes, with perfect logic, that the two bolts of lightning were simultaneous. For Anna, the events lightning strikes the front tree and lightning strikes the rear tree happened at the same time. They share a single now. But now, let us shift our perspective to Ben, inside the moving train. What does he see? At the moment the lightning strikes, he is also exactly halfway between the points where the light will enter his window. However, he is moving rapidly toward the location of the forward flash and away from the location of the rear flash. The light from the bolt that struck the tree in front of the train is racing toward him at speed times c*. But because Ben and his train are moving toward that oncoming light pulse, the distance the light has to travel to reach him is decreasing. Conversely, the light from the bolt that struck the tree behind the train is also racing toward him at speed times c*. But because Ben is moving away from it, the light has to chase him down, covering a greater distance to reach his eyes. Since the speed of light is constant and does not compensate for the motion of the source or the observer, the outcome is inevitable. The light from the forward lightning strike will reach Ben before the light from the rear lightning strike. He will see a flash from the front, and then, A moment later, a flash from the back. His direct sensory experience is of two distinct, separate events. If you are still awake, consider what Ben must conclude. He knows he is sitting in the center of the train carriage. He receives two light signals, but they are not received together. The only logical conclusion he can draw, based on the constant speed of light, is that the two lightning bolts did not strike at the same time. From his perspective, the forward bolt struck first, and the rear bolt struck a little later. For Ben, there was no single now encompassing both strikes. The events that were simultaneous for Anna are, for Ben, sequential. This is not an illusion of perception. It is not a trick of the light. It is a fundamental statement about reality. There is no universal privileged clock that can define a true sequence for these two events. The question, which bolt actually struck first, has no absolute answer. The answer depends entirely on your state of motion. Anna, at rest relative to the embankment, measures them to be simultaneous. Ben, moving relative to the embankment, measures them to be not simultaneous. Both are correct. There is no God's eye view from which to judge one perspective as truer than the other. The flow of time is not a single river. It is a vast delta, with each observer following their own unique channel of now. This relativity of simultaneity is the direct and inescapable price of having a universal speed limit for light. It is the mechanism by which the universe enforces the principle that no inertial frame is preferred. It shatters the Newtonian idea of a single, universal present that sweeps across the cosmos. Your now is not my now if we are in relative motion. This concept is the gateway to all the other strange effects of relativity. It is the first and most crucial step in realizing that time and space are not separate, rigid backgrounds, but are malleable and deeply intertwined components of a single entity. The fabric of reality is not what we thought. If simultaneity is relative, it forces us to reconsider the very nature of time itself. The personal, frame-dependent nature of now leads us directly to an even more startling prediction, that time itself does not flow at the same rate for everyone. This leads us to our next profound concept, one that has captured the human imagination like no other in physics: time dilation. Time dilation. In our last lesson, we discovered that the very idea of now is not universal, but personal, dependent on one state of motion. This was the first crack in the ancient edifice of absolute time. Now, we follow that crack to its astonishing conclusion. If two observers cannot agree on which events are simultaneous, then they cannot possibly be using the same clock. They must, in fact, be experiencing the flow of time itself at different rates. This phenomenon is known as time dilation, and it is one of the most celebrated and verified predictions of Einstein's theory. To understand why this must be so, let us construct the most reliable clock we can imagine, one based on the one universal constant we have, the speed of light. We will build a light clock. Picture a simple device, two perfect mirrors, facing each other, separated by a fixed distance. A single pulse of light bounces continuously between them. One round trip from the bottom mirror to the top and back again constitutes one tick of this clock. It is a pristine, fundamental timekeeper. Now, let us place this clock aboard a spacecraft, moving at an immense, constant velocity, a significant fraction of the speed of light, relative to an observer on a nearby space station. First, consider the perspective of an astronaut inside the spacecraft, sitting right next to the light clock. For her, the clock is at rest. The light pulse simply travels straight up and straight down, covering a distance equal to twice the separation between the mirrors for each tick. She measures the time for one tick as being the distance traveled, divided by the speed of light. This time, measured by an observer at rest relative to the clock, is given a special name, the proper time. It is the fundamental, intrinsic tick rate of the clock itself. Now, let us shift our perspective to the observer on the space station, watching the spacecraft whip past him. From his vantage point, the story is very different. As the light pulse leaves the bottom mirror and travels upward, the spacecraft is moving horizontally, Therefore, from his frame of reference, the light pulse does not travel straight up and down. Instead, it follows a zigzag path, a longer, diagonal trajectory. To visualize this, imagine a ball being bounced straight up and down in a train. To someone outside the train, the ball follows a series of parabolic arcs. For the light pulse, the principle is the same, but the implications are profound. Here is the crux of the matter, the point where Einstein's second postulate does its revolutionary work. The speed of light is constant. The astronaut inside the ship and the observer outside both measure the speed of that light pulse to be exactly the same value, *c*. But they disagree on the distance the light has traveled to complete one tick. The outside observer sees the light taking a longer, the diagonal path. Since speed is distance divided by time, and the speed is fixed, the only possible conclusion is that more time must have passed for the longer path. If the distance is longer and the speed is the same, the time elapsed must be greater. Let that concept settle in. The outside observer, watching the moving clock, measures its tick to take longer than the tick measured by the astronaut traveling with it. From his perspective, time itself aboard the moving spacecraft is flowing more slowly. The clocks are ticking less frequently. All processes are running in slow motion. This is not a mechanical defect. It is not an illusion caused by the finite speed of light. It is a real, physical effect on time itself. A clock moving relative to you is measured to run slow compared to your own stationary clocks. This slowing of time is quantified by a mathematical expression known as the Lorentz factor, named after the physicist Hendrik Lorentz. The factor depends only on the relative velocity between the two observers. At everyday speeds, like those of a car or an airplane, the effect is infinitesimally small, utterly negligible. But as the relative velocity increases, approaching the cosmic speed limit of light, the effect becomes dramatic. At 87% of the speed of light, time would be flowing at half its normal rate. At 99.5% of light speed, it would slow to a tenth. And as the velocity approaches the speed of light itself, the Lorentz factor mathematically stretches towards infinity, suggesting that time for the moving object would, from our perspective, appear to come to a complete standstill. A fascinating and crucial aspect of this is its reciprocity. Just as the observer on the space station sees the spacecraft's clocks running slow, the astronaut on the spacecraft would see the space station's clocks running slow. Each views the other as being the one in motion, and thus, each views the other's time as being dilated. This seems like a paradox, but it is perfectly consistent. Simultaneity is relative, and so are measurements of time intervals. The only way to resolve who has actually experienced less time is if the two observers are reunited, which would require acceleration, moving us into the realm of general relativity and the famous twin paradox. But for now, know that this is not science fiction. Time dilation is a confirmed daily reality. Particle accelerators like the Large Hadron Collider rely on it. Unstable subatomic particles called muons, created when cosmic rays strike our atmosphere, have such short lifetimes that they should decay before reaching the Earth's surface. But because they are traveling at nearly the speed of light, their internal clocks are dramatically slowed from our perspective, allowing them to survive the journey and be detected. The very GPS system in your phone would accumulate errors of several miles per day if the engineers did not constantly correct for the fact that the clocks on the satellites in orbit are running at a slightly different rate than clocks in the ground, due to both their speed and their position in Earth's gravity well. The universe truly operates this way. Time is not the only thing that changes with motion. Just as we have time dilation, we must also consider the effect on space itself, a complementary phenomenon known as length contraction. Length contraction. We have just explored how time, once thought to be an absolute river, is revealed to be a flexible stream, its current slowing for objects in motion. Now, as you rest in this state of open awareness, we must turn to the other side of this relativistic coin. If time is not absolute, then space cannot be the rigid fixed stage we once imagined. The same theory that gives us time dilation necessarily implies a complementary phenomenon, length contraction. This is the concept that an object's length, measured in its direction of motion, is not a fixed property, but depends on who is measuring it, and how fast they are moving relative to the object. To understand why this must occur, let us return to our thought experiment with the spacecraft and the space station. Imagine now that the astronaut aboard the spacecraft wishes to measure its own length. She has a simple method. She places a mirror at the very front of the ship's hull and one at the very rear. She then stands precisely in the middle, equipped with a laser and a perfect clock. She fires a laser pulse towards both mirrors simultaneously. Since she is exactly in the center and the speed of light is constant, the pulses will return to her at the very same instant. From this, she can confidently calculate the length of her spacecraft. This length, measured in the rest frame of the object itself, is given a special name, just like proper time. It is called the proper length. It is the true intrinsic length of the object, the length you would measure if you were holding a ruler against it while it was stationary. Now, let us shift our perspective to the observer on the space station, watching this same spacecraft fly past at a tremendous speed. He also decides to measure the length of the spacecraft. How does he do this? He must mark the positions of the front and the back of the spacecraft at the same time, according to his own frame of reference. He sets up two precise synchronized clocks along his station and, at a predetermined instant, records where the nose and the tail of the spacecraft are. The distance between these two marks is the length of the spacecraft as he measures it. But here, we immediately encounter the relativity of simultaneity. The event of marking the position of the nose and the event of marking the position of the tail, which are simultaneous for the observer on the space station, are not simultaneous for the astronaut on the spacecraft. From her point of view, the outside observer is marking the position of the nose first and the tail a moment later. In the brief interval between those two events from her perspective, the spacecraft has moved forward. Therefore, she would see the outside observer measuring the distance between where the nose was at one moment and where the tail was a little later. This measured distance would be shorter than her own proper length. Let us use a more concrete analogy. Imagine the spacecraft is a subway train and the outside observer is standing on a platform. To measure the moving train's length, he must paint a mark on the platform when the front of the train passes him, and another mark when the back of the train passes him. But for his measurement to be valid, he must use a single clock to define these two events. Now, consider the perspective of a passenger sitting in the exact center of the moving train. She would insist that the two paint marks were not made at the same time. She would see the mark for the front of the train being made first, and then, after the train has moved forward, the mark for the back of the train being made later. The distance between these two marks, made at different times from her perspective, would indeed be shorter than the length of the train as she knows it. This is the essence of length contraction. It is a direct and necessary consequence of the relativity of simultaneity. Because the two events used to measure the length, noting the position of the front and the back, cannot be simultaneous in both frames of reference, the resulting measurement of length will differ. The fundamental rule is this: an object is measured to be longest in its own rest frame. Any observer moving relative to the object will measure it to be shorter or contracted along its direction of motion. The amount of contraction is governed by the very same Lorentz factor that dictates time dilation. The faster the relative motion, the greater the contraction. At everyday speeds, this effect is immeasurably tiny, but as an object approaches the speed of light, its length in the direction of motion, as measured by a stationary observer, would appear to shrink towards zero. It is crucial to understand that this is not an illusion, nor is the object being physically crushed. The contraction is a real feature of spacetime geometry, as measured between two different frames of reference. Furthermore, the contraction only occurs in the dimension parallel to the direction of motion. The height and width of the object remain unchanged. A speeding sphere would be measured as an oblate spheroid, a sphere flattened along its direction of travel, while a cube would become a rectangular slab. This phenomenon, like time dilation, has been verified experimentally. For physicists working with particle accelerators, it is a daily reality. They must account for the fact that the bunches of particles, like protons, are length contracted from the perspective of the laboratory. For a proton moving at 99.999999% the speed of light in the Large Hadron Collider, the 27-kilometer ring itself would appear dramatically length contracted from the proton's point of view, perhaps to just a few dozen meters. This contraction is as real to the proton as the stretching of time. It is the universe ensuring that the laws of physics, including the constant speed of light, hold true for every observer. So, we now have our two twin effects. Moving clocks run slow, and moving rulers are measured to be short. These are not separate curiosities, but two sides of the same coin. They are the manifestations of a deeper, unified reality. We have been treating space and time as if they were independent, but our journey has been leading us to an inescapable conclusion: they are not separate at all. With our understanding of space and time now deeply intertwined, we can no longer view them as separate entities. They are woven together into a single, four-dimensional fabric, which is the true stage for our universe. This unified entity is known as spacetime, the Spacetime Continuum. We have now journeyed through the strange and counterintuitive landscapes of relative simultaneity, time dilation, and length contraction. We have seen that time is not a universal constant, and that space is not a fixed stage. As you rest here, in the quiet between thoughts, let us now weave these separate threads into a single, magnificent tapestry. The separate concepts of space and time, which have guided human thought for millennia, are not fundamental. They are merely perspectives, partial views of a deeper, unified reality. This reality is a four-dimensional continuum known as space-time. To understand this unification, let us first recall our classical intuition. In the world of Newton, we would describe an event by saying where it happened and when it happened. The where required three numbers, perhaps its latitude, its longitude, and its altitude, its location in the three-dimensional arena of space. The when was a separate piece of information, a single number read from a master clock. These were two distinct categories of information. But special relativity has shown us that these categories are not independent. Your measurement of time intervals depends on your motion through space, and your measurement of spatial lengths depends on your state of motion in time. They are inextricably linked. The mathematician Hermann Minkowski, building directly on Einstein's 1905 paper, was the first to formalize this breathtaking synthesis. He famously declared, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." He proposed that we live in a four-dimensional world. Three of these dimensions are the familiar ones of space: length, width, and height. The fourth dimension is time. This is not time as a sequence of nows, but time as a dimension, just as real and physical as the spatial ones. Every event, every occurrence in the universe, is a point in this four-dimensional continuum. It is not just the bother and now. Let that idea settle in. The you that is listening to this is not just a body in a room. You are a complex, evolving path through space-time. Think of your life not as a series of fleeting moments, but as a long, unique thread stretching from the event of your birth to this present moment and onward into the future. Physicists call this thread your world line. It is your entire history and future, all laid out in the four-dimensional space-time continuum. When you are stationary, sitting in a chair, you are still moving relentlessly through the time dimension. Your world line is a nearly straight line through time. When you get up and walk across the room, your world line begins to weave through the spatial dimensions as well, tracing a gentle, curving path through the four-dimensional fabric. This view resolves the seeming paradoxes of relativity. Why can two observers disagree on the time between two events, or on the distance between 2 points? It is because they are slicing the four-dimensional spacetime block at different angles. Imagine a long four-dimensional loaf of bread where the length of the loaf represents the time dimension. Two events are like two raisins embedded within this loaf. One observer, moving at one velocity, will make a slice through the loaf, a three-dimensional cross-section they call space, at a single moment that cuts through both raisins at what they call the same time. Another observer, moving at a different relative velocity, will hold their knife at a different angle. Their slice of now will cut through the first raisin at one point and the second raisin at a different point. They are both looking at the same four-dimensional reality, but their individual perspectives, their individual states of motion, cause them to dissect it into space and time in different ways. The space-time interval between the two raisins, a combination of their separation in space and time, is what remains absolute and agreed upon by all. This concept of space-time is the true stage upon which the universe is built. It is a static, four-dimensional manifold containing all that ever was and all that ever will be. The feeling of a flowing now, the passage of time, is, in this view, a profound and personal psychological experience, a consciousness moving along its own world line, rather than a fundamental property of the universe itself. This can be a challenging concept to sit with, but it is the most accurate description we have of reality at this level. The space-time of special relativity, as conceived by Minkowski, is flat and static. It is the arena for events, but it is not yet dynamic. It does not yet react to the presence of matter and energy. But by creating this unified stage, Minkowski and Einstein provided the essential language, the precise geometry, for the next great leap. The stage itself, they would soon discover, was not merely a passive backdrop. It could be warped, curved, and dynamic. The geometry of this stage would become the very embodiment of gravity. If you are still awake, picture this not as an abstract mathematical concept, but as a new way of seeing. You are not in a place, at a time. You are an event in space-time. Your entire life is a beautiful, intricate world line woven into the fabric of the cosmos. This is the foundational insight that elevates physics from a description of things moving in space and time to a description of the geometry of space-time itself. The space-time of special relativity is flat and unchanging. It beautifully describes the universe for observers moving at constant velocities. But Einstein realized it was incomplete, as it could not describe the force we feel every moment, the force that governs the cosmos, gravity. To incorporate gravity, he would have to make the stage itself dynamic. This leads us to his masterwork, the general theory of relativity. The equivalence principle. We have now reached a pivotal moment in our journey. We have mastered the landscape of special relativity, a world of constant velocities, flat space-time, and the universal speed of light. But as you rest here, a force is acting upon you, a gentle, unyielding pull that has been with you since the moment you were born. Gravity. Special relativity, for all its brilliance, could not describe it. Gravity, in Newton's view, was a mysterious, instantaneous force at a distance, a concept that Einstein found deeply unsatisfying. His quest to reconcile gravity with his new understanding of space-time led him to what he would later call the happiest thought of my life. This thought is the gateway to his general theory of relativity, and it is known as the equivalence principle. The equivalence principle is a statement of profound simplicity, yet its consequences are universe-altering. It proposes that there is no measurable difference, no experiment you can perform that can distinguish between the effects of a uniform gravitational field and the effects of a constant acceleration. Let us unpack this carefully. Imagine you are in a small, windowless room, like an elevator car. You feel a firm pressure on your feet. If you drop a set of keys, they fall straight to the floor. Now, is this room sitting stationary on the surface of the Earth, with gravity pulling you down? Or is it actually in the vacuum of deep space, being accelerated by a rocket at a constant rate of 9.8 meters per second squared. The equivalence principle states that, within the confines of your room, there is absolutely no experiment you can perform, mechanical, electrical, or optical, that would allow you to tell the difference. The experience of weight in a gravitational field is perfectly equivalent to the experience of being pressed into the floor of an accelerating vehicle. This was Einstein's happy thought. He realized that gravity, in a local context, could be transformed away by simply adopting a freely falling frame of reference. If your elevator car were in free fall, its cables cut, you would feel weightless. Objects would float beside you. From your perspective, inside the falling box, gravity would have vanished. This is not because gravity has ceased to exist, but because you and the elevator are now accelerating downward at the same rate, cancelling its local effects. This simple symmetry between acceleration and gravity became the foundational stone upon which he would build his new theory. Now, let us take this principle and push it to its logical conclusion, as Einstein did. Let us return to our accelerating rocket ship in deep space. Suppose a beam of light enters a small hole in the side of the ship, traveling in a perfectly straight line across the cabin to hit the opposite wall. From the perspective of an inertial observer outside, watching the ship accelerate, the path of the light is indeed a straight line. But from your perspective inside the accelerating ship, something different happens. In the tiny amount of time it takes for the light to cross the cabin, the ship itself has moved upward. Therefore, the spot where the light hits the far wall will not be directly across from the hole it entered. It will be a little closer to the floor. To you, inside the ship, the path of the light beam will appear to curve downward. Now, invoke the equivalence principle. If the effects of acceleration are indistinguishable from the effects of gravity, then this curved path of light must also occur in a gravitational field. Therefore, Einstein predicted that a beam of light, as it passes through a gravitational field, will not travel in a perfectly straight line. Its path will be bent. This was a staggering prediction. For centuries, light was thought to be massless and therefore immune to gravity. Newton's theory could not account for this. But here was Einstein, using pure thought, concluding that gravity must bend light. This was not a force pulling on light. It was a consequence of the very nature of spacetime under the influence of gravity, as suggested by the equivalence of acceleration and gravity. This principle also leads to another profound implication: gravitational time dilation. Imagine our accelerating rocket ship again. Suppose two pulses of light are sent from the floor to the ceiling. From the perspective of an outside observer, the light travels at a constant speed, *c*. But from inside the ship, the ceiling is accelerated toward the point where the first pulse was emitted. This means the ceiling, by the time it receives the second pulse, has a different velocity relative to the first pulse. This change in velocity, according to the Doppler effect, means the frequency of the light pulses received at the ceiling will be different from the frequency at which they were emitted at the floor. By the equivalence principle, this must also happen in a gravitational field. Light climbing out of a gravitational well will lose energy, not by slowing down, but by shifting to a longer, redder wavelength. This is the phenomenon of gravitational redshift. And since the frequency of light is a kind of clock, think of it as the ticking of an electromagnetic wave. This means that time itself must run slower in a stronger gravitational field. A clock at sea level, where gravity is stronger, will tick more slowly than an identical clock on a mountaintop. So, from one simple happy thought, we have derived two of the most dramatic predictions of modern physics: that gravity bends light and that gravity warps time. The equivalence principle is the conceptual bridge that allowed Einstein to move from the flat, static spacetime of special relativity to a new vision where gravity is not a force, but a manifestation of the geometry of spacetime itself. It suggested that the presence of mass and energy must somehow curve the four-dimensional fabric of the universe, and that what we perceive as gravity is simply the motion of objects following the straightest possible paths through this curved geometry. If acceleration is indistinguishable from gravity, then perhaps gravity is not a force at all, but a consequence of geometry. This realization leads us to the very heart of general relativity, where the stage of spacetime itself becomes the central actor. Gravity as the geometry of spacetime. We have now crossed the conceptual bridge of the equivalence principle. We have seen that the effects of acceleration are indistinguishable from the effects of gravity, and that this implies light must bend and time must warp in a gravitational field. This was the crucial clue that led Einstein to his grand synthesis. Now, as you rest in the quiet of the night, we arrive at the very heart of general relativity, the core idea that redefines our understanding of the cosmos. Gravity, we will discover, is not a force in the traditional sense. It is not a mysterious pull acting across space. Instead, gravity is the geometry of spacetime itself. It is the shape of the cosmic stage, and what we perceive as gravitational attraction is merely the motion of objects following the straightest possible paths through a curved landscape. To grasp this, we must first let go of Newton's apple. The apple does not fall because the Earth reaches out with an invisible force to grab it. Instead, imagine that the presence of the Earth, due to its mass, alters the very fabric of spacetime around it. The most common analogy, though imperfect, is immensely helpful. Picture a vast, taut, two-dimensional rubber sheet. This sheet represents the fabric of spacetime. Now, place a heavy bowling ball in the center of this sheet. The ball creates a deep depression, a curvature in the sheet. This is what mass does to spacetime. It warps it, creating dips and wells. The more massive the object, the deeper the well. The Sun, for instance, sits in the center of a profound gravitational well in the spacetime of our solar system. Now, take a small marble and set it rolling near the bowling ball. Instead of traveling in a straight line, the marble will spiral inward, tracing a curved path around the central mass. From a perspective above the sheet, it seems as if the bowling ball is attracting the marble. But there is no pull. The marble is simply following the contours of the curved surface. It is moving along the straightest path possible given the geometry of the terrain. This straightest path on a curved surface has a name, a geodesic. On the curved surface of the Earth, a geodesic is a great circle route, like the path an airplane takes between continents. In the curved spacetime of the universe, the geodesic is the path of an object upon which no other forces are acting. This is the monumental shift in understanding. Einstein's field equations, the complex mathematical heart of general relativity, provide the recipe for how mass and energy, the actors on the stage, tell spacetime how to curve. And the curvature of spacetime, the shape of the stage itself, then tells those actors how to move. The Earth orbiting the Sun is not being pulled by a force. It is simply following a geodesic, a free-fall path through the curved spacetime created by the Sun's mass. It is, in a very real sense, constantly falling around the Sun, just as an astronaut in the International Space Station is falling around the Earth. In both cases, they are following the straightest possible line through a curved four-dimensional universe. This geometric view seamlessly explains what Newton's force could not. Recall the bending of starlight. A beam of light from a distant star, passing near the Sun, does not feel a gravitational pull. Instead, it is simply following its own geodesic, its own straight-line path. But because the spacetime through which it travels is curved by the Sun's mass, that geodesic itself is a curved path through the space around us. Light, in its unwavering commitment to travel the shortest distance between 2 points in spacetime, has its trajectory bent. It is as if the straightest line on our cosmic map has been drawn on a curved surface. This framework also resolves the mystery of action at a distance that so troubled Newton. In his theory, gravity was instantaneous. If the Sun were to suddenly vanish, the Earth would instantly fly off in a straight line. But in Einstein's universe, nothing can travel faster than light, not even information about gravity. The Sun's mass creates a curvature in spacetime. Changes in that mass, like the Sun disappearing, would create a ripple, a wave in the spacetime fabric that propagates outward at the speed of light. The Earth would continue in its orbit for approximately 8 minutes, the time it takes light to travel from the Sun, until the gravitational wave, the news of the Sun's demise, reached it and the space-time around it flattened out. Gravity is local. It is the geometry of the space you are in at this very moment. So, let this new vision of the universe settle in your mind as you drift towards sleep. The force that holds you to your bed, that guides the planets in their dances, that governs the motion of galaxies, is not a force at all. It is geometry. The universe is not a collection of objects in a void, pushing and pulling on one another. It is a dynamic, flexible, four-dimensional continuum whose shape is molded by its contents and whose contours guide every particle of matter and every ripple of light. We are all, from the smallest dust mote to the most massive star, simply travelers moving along the geodesics of a curved and magnificent space-time. This new geometric description of gravity was not just a philosophical improvement. It made several precise, testable predictions that differed from Newton's theory. The first and most immediate of these tests involved a tiny, long-standing anomaly in the orbit of the innermost planet, Mercury. The first test, the precession of Mercury's perihelion. As we continue our journey, we now arrive at a critical moment, the first concrete test that would pit Einstein's new geometric theory of gravity against the established might of Newton's. For any new scientific theory to be taken seriously, it must not only explain what the old theory could, but it must also resolve a known anomaly, a persistent crack in the old foundation that had stubbornly refused to be sealed. For general relativity, that crack was a tiny, inexplicable drift in the orbit of the planet Mercury. This was a problem that had troubled astronomers for decades, a ghost in the celestial machinery. And it was here that Einstein's vision of curved spacetime would achieve its first and most personal victory. To understand the nature of this anomaly, we must first picture a planet's orbit around the Sunday. In the perfect, idealized two-body system of Newtonian gravity, a planet would trace a static, closed ellipse, returning to the exact same starting point with each and every orbit, like a cosmic clockwork. The point of its closest approach to the Sun, known as the perihelion, would remain fixed in space forever. But our solar system is not a perfect, isolated system. It is a bustling, dynamic place. The other planets, particularly the massive Jupiter, exert their own gravitational tugs on Mercury, subtly perturbing its orbit. Because of this, Newtonian physicists knew that Mercury's elliptical path should not be perfectly fixed. Instead, the entire ellipse should slowly rotate or precess around the Sun over time. This means that the point of perihelion shifts slightly with each orbit, tracing out a very slow, graceful circle over centuries. This is known as the precession of the perihelion. Throughout the 19th century, astronomers, most notably Urbain Le Verrier, had meticulously observed and calculated this precession. They could account for nearly all of it using Newton's laws and the gravitational influence of the known planets. But there was a problem. After all the calculations were done, after every known gravitational pull was factored in, a tiny discrepancy remained. The observed precession of Mercury's orbit was larger than the Newtonian prediction by an amount of 43 arcseconds per century. Now, an arcsecond is an almost vanishingly small unit of measurement. It is 1/3000/600th of a degree. To visualize this, the 43 arcseconds per century discrepancy is equivalent to the angular width of a human hair held at arm's length, but observed over a 100-year span. It was a minuscule amount, but it was real, it was persistent, and it was unexplained. For decades, physicists proposed various solutions. Some suggested the existence of an unseen planet, dubbed Vulcan, orbiting inside Mercury's path. Others postulated a ring of dust around the Sunday. But despite extensive searches, no such planet or ring was ever found. The 43 arcseconds remained an unsolved mystery, a nagging reminder that our understanding of gravity might be incomplete. This was the problem that Einstein turned to with his new theory. He began applying his field equations, the the complex mathematical description of how mass and energy curve, spacetime, to the space around the Sunday. In Newton's universe, the Sun creates a simple, static gravitational field. But in Einstein's universe, the Sun creates a curvature in the four-dimensional fabric of spacetime. Near a massive body, this curvature is not static. The theory predicted that the orbits of planets would not be perfect, closed ellipses. Instead, the path itself should be a rosette pattern, a slowly precessing ellipse, because the planet is following a geodesic in a spacetime whose curvature changes slightly with distance from the Sunday. The geometry itself dictates that the orbit cannot quite close upon itself. With great anticipation, Einstein performed the calculation. The result was elegant and precise. His equations, derived purely from the geometry of spacetime, predicted that the perihelion of Mercury should precess by an extra amount above and beyond the Newtonian perturbations, due solely to the curvature of spacetime. And what was that amount? It was exactly 43 arcseconds per century. The number matched the observational anomaly perfectly. It is said that upon seeing this result, Einstein felt a profound sense of excitement, that his heart palpitated with the thrill of the discovery. The tiny ghost in the machine had been exorcised, not by inventing a new planet or adding a fudge factor, but by revealing a deeper layer of reality. This was more than just a successful prediction. It was a moment of profound scientific beauty. For centuries, Mercury had been faithfully following the geodesic path dictated by the Sun's curvature. Astronomers had been meticulously recording its path, unaware that they were documenting the signature of curved spacetime itself. Einstein, with a piece of chalk and a blackboard, had finally decoded that signature. The orbit of Mercury was no longer an anomaly, it was a confirmation. It was the first direct evidence that the universe operates according to the rules of general relativity, that gravity is indeed the geometry of spacetime. A problem that had withstood the best efforts of Newtonian physics for over half a century had yielded completely and precisely to a new, more profound vision of the cosmos. Having passed one test with flying colours, general relativity now faced an even more dramatic and public one. Its prediction that starlight would be bent by the Sun's gravitational field was a bold claim that could be tested only during a rare celestial event, a total solar eclipse. Gravitational lensing, the bending of light. Having resolved the subtle mystery of Mercury's orbit, Einstein's general relativity now prepared for a more public and spectacular test. The theory made a bold, almost fantastical prediction that the path of light itself would be bent by gravity, or, to use our new language, that light would follow the curved geodesics of warped spacetime. This phenomenon, which we now call gravitational lensing, would become one of the most powerful tools in all of astronomy, but in 1919 it was a stark prediction that needed proof. And the key to that proof lay in the temporary daytime darkness of a total solar eclipse. Let us first solidify the concept. We have already seen, through the Equivalence Principle, why this must be true. If an accelerating spaceship causes a light beam to curve from the perspective of someone inside, then gravity must do the same. And in the geometric view of general relativity, this is not a force tugging on light, a nonsensical idea, since light is massless, but a simple consequence of geometry. Imagine spacetime around a massive object like the Sun as a curved, flexible sheet. Now, picture a beam of light as a marble rolling swiftly across that sheet. The marble will naturally follow the curvature, its straight-line path becoming a curved trajectory as it passes near the depression caused by the mass. The light is simply taking the shortest available path through a curved landscape. The greater the mass, the deeper the curvature, and the more pronounced the bending. Einstein calculated that starlight grazing the limb of the Sun should be deflected by a very specific, small, but measurable angle, 1.75 arcseconds. This was precisely twice the value that a naive Newtonian calculation, treating light as a particle with mass, might have suggested. The universe, it seemed, was fully Einsteinian. But how does one measure the bent path of starlight? The sun, in all its brilliant fury, makes this impossible under normal conditions. Its overwhelming glare drowns out the delicate pinpricks of distant stars. The solution, provided by nature itself, is a total solar eclipse. During these brief, precious moments, the moon slides perfectly between the Earth and the sun, blocking its blinding photosphere and revealing the sun's faint, wispy corona. In this sudden celestial twilight, the stars surrounding the sun become visible in the daytime. The plan, then, was straightforward in concept, but immensely challenging in execution. To photograph the star field around the sun during a total eclipse and compare it to a photograph of the exact same star field taken at night, months later, when the sun is in a different part of the sky. If Einstein was correct, the stars whose light passed close to the sun would appear to be in slightly different positions compared to their nighttime photographs. They would seem to have been pushed outward, away from the sun's mass, because their light had been bent on its journey to our telescopes. The responsibility for this monumental task fell to the British astronomer Arthur Eddington, a passionate early adherent of Einstein's theory. The date was the 29th of May 1919. Eddington led 2 expeditions to optimal viewing locations for the eclipse, one to the island of Principe, off the coast of Africa, and another to Sobral in Brazil. The world watched, and the scientific community held its breath. The expeditions were plagued with anxiety. On Principe, Eddington's team battled clouds until moments before totality. They managed to take a series of photographic plates through a break in the cloud cover. Back in England, the painstaking process of measuring the star positions on the eclipse plates and comparing them to the reference plates began. The results from Sobral were clearer and ultimately more decisive. The measurements revealed a shift in the star positions that matched Einstein's prediction of 1.75 arcseconds. Newton's universe, which had governed scientific thought for over 2 centuries, had been superseded. When the results were announced that November, they caused a global sensation. The front page of the Times of London proclaimed, "Revolution in Science, a new theory of the universe." Einstein instantly became a worldwide celebrity, a symbol of genius whose name transcended the confines of academic science. It was a triumph of human reason, a validation of a theory born from pure thought, now confirmed by the precise alignment of the cosmos. The light from distant stars had, indeed, curved along the warped space-time around our sun, and in doing so, had illuminated a new path for physics. Today, gravitational lensing is far more than a confirmed prediction. It is a cornerstone of modern observational astronomy. We no longer need to wait for eclipses. We observe what is called strong lensing, where a massive galaxy cluster acts as a powerful cosmic lens, bending and distorting the light from galaxies far behind it into spectacular arcs and rings, like a vast magnifying glass in space. This allows us to see objects that are otherwise too distant and faint to detect, peering deeper into the universe than ever before. We also measure weak lensing, where the subtle distortion of millions of galaxy shapes by intervening dark matter allows us to map the invisible cosmic web that constitutes most of the matter in the universe. And there is even microlensing, used to detect planets around distant stars, as their gravity creates a tiny, temporary brightening of a background star's light. From a single, bold prediction tested in the shadow of the moon, gravitational lensing has grown into an entire field of study, allowing us to see the invisible and study the farthest reaches of space and time. If gravity can bend light, warping its path through space, it can also affect the very essence of the light itself, its energy and its frequency. This leads us to another profound implication of gravity's grip on space-time, one that affects time itself: the phenomenon of gravitational redshift, gravitational time dilation, and redshift. We have seen how gravity, as the geometry of space-time, bends the path of light, but its influence runs deeper still, touching not just the road that light travels, but the very nature of the traveler itself. As you rest here, the force of gravity is doing more than holding you to the earth. It is subtly influencing the flow of time in the space you occupy. This leads us to two intimately related phenomena: gravitational time dilation and its luminous signature, gravitational redshift. These concepts reveal that gravity affects not only where light goes, but what light is. To understand this, let us return to the bedrock of our understanding, the equivalence principle. Imagine once more our windowless elevator, but this time, let us equip it with a precise light source on the floor and a detector on the ceiling. The source emits light of a specific pure frequency, which we can think of as a very specific color, say, a vibrant green. Now, let us place this elevator in deep space and accelerate it upwards at a constant rate, equivalent to the gravity on Earth. As the light pulse travels from the floor to the ceiling, it takes a finite amount of time to make the journey. In that tiny fraction of a second, the ceiling of the elevator has accelerated upward, moving toward the point where the light pulse was emitted. From the perspective of someone inside the accelerating elevator, this acceleration has a curious effect. The detector on the ceiling is moving toward the light source, relative to the light's initial path. This motion compresses the light waves, very much like the Doppler effect that makes a siren's pitch rise as an ambulance moves toward you. The detector at the ceiling, therefore, measures the light to be slightly bluer, of a higher frequency, than what was emitted at the floor. Now, by the equivalence principle, what is true for acceleration must be true for gravity. We therefore must conclude that in a gravitational field, light climbing upward will undergo a reverse process. As a beam of light struggles against a gravitational field, it loses energy, but since the speed of light is constant, it cannot slow down. Instead, it loses energy by shifting to a longer, and therefore redder, wavelength. This is the phenomenon of gravitational redshift. A light beam emitted from the surface of a massive star and received by a distant telescope will be measurably redder than the same light emitted in the weak gravity of empty space. The light is not tired, it is simply encoded with the story of its climb out of a gravitational well. But this shift in light has a far more profound implication for the fabric of reality itself. Light, with its unwavering frequency, is one of the most perfect clocks we can imagine. Each oscillation of the electromagnetic wave is a tick of a fundamental clock. If gravity changes the frequency of light, then it is, by definition, changing the rate at which time passes. This is gravitational time dilation. Time itself runs slower in a stronger gravitational field. Imagine two identical perfect clocks. One is placed on the surface of the Earth, deep within its gravitational well. The other is placed on a high mountain peak, or better yet, on a satellite in orbit, where Earth's gravity is slightly weaker. The clock in the stronger gravitational field, the one at sea level, will tick more slowly than the clock in the weaker field. The difference is infinitesimally small for Earth's gravity, but it is real and measurable. You can picture space-time as a stretched, flexible trampoline. A clock placed in a deep curve in that fabric will experience time at a slower rate compared to a clock on a shallower, flatter region. The deeper the gravitational well, the more stretched the space-time, and the more time is diluted. This is not a mechanical error or an illusion. It is a direct result of the curvature of the four-dimensional continuum. The time dimension itself is being warped along with the spatial dimensions. The real-world evidence for this is all around us, built into the technology we use every day. The Global Positioning System, GPS, is a network of satellites, each containing an extraordinarily precise atomic clock. These satellites are in a region where Earth's gravity is measurably weaker than on the surface. According to general relativity, the clocks on these satellites should run faster by about 45 microseconds per day due to gravitational time dilation. However, they are also moving at high speed, and special relativity tells us that their velocity should cause them to run slower by about 7 microseconds per day. The net effect is that the satellite clocks gain about 38 microseconds each day compared to clocks on the ground. If the engineers at NASA did not deliberately build this correction into the system, the GPS would accumulate errors of over 10 kilometers per day rendering it useless. Your phone's ability to guide you is a continuous silent affirmation of Einstein's theory, a daily correction for the fact that time flows at different rates in the sky than it does on the ground. The effects become far more dramatic as we look out into the cosmos. The light from the surface of a dense white dwarf star is noticeably redshifted, and for a theoretical observer watching an object fall toward the event horizon of a black hole, the light would redshift so dramatically that it would fade into utter blackness, while time for the falling object would appear to grind to a complete halt from the outside perspective. Gravitational time dilation is the universe's way of telling us that time is not a universal metronome. It is a local phenomenon, a personal experience shaped by the geometry of the space one occupies. Gravitational time dilation and redshift show us that mass and energy can warp the very fabric of space-time, creating ripples in the gravitational field itself. But general relativity predicts that the most dramatic events in the cosmos can do more than create static curves. They can send actual ripples across this fabric, waves that travel through space-time itself. These are known as gravitational waves. Gravitational waves. We have explored how mass and energy curve the stage of space-time, creating the effects we perceive as gravity. We have seen how this curvature bends light and stretches time. But what happens when the most massive objects in the universe undergo a violent, catastrophic change? According to general relativity, the stage itself does not simply adjust silently, it ripples. Like a drumhead struck by a mighty blow, the fabric of space-time can vibrate, sending out waves of curvature that travel at the speed of light across the cosmos. These are gravitational waves, and their discovery opened an entirely new sense with which we can perceive the universe. The concept is a direct prediction of Einstein's equations. In 1916, just a year after finalizing his theory, he realized that his field equations had wave-like solutions. Imagine the calm surface of a pond. This is flat, undisturbed space-time. Now, toss a pebble into the center. Ripples spread outwards in concentric circles. A gravitational wave is analogous to that ripple, but it is a ripple in the four-dimensional fabric of space-time itself. The pebble is not a simple stone, but an accelerating mass. However, for the ripples to be significant, the acceleration must be immense, and the mass must be enormous. The everyday motion of planets and stars produces gravitational waves so unimaginably faint that they are completely undetectable. The waves we seek are born from the most extreme events in nature, from supernova explosions that tear stars apart, from neutron stars spinning rapidly around one another, and most powerfully, from the final in-spiral and cataclysmic merger of two black holes. These waves are not like any we are familiar with. A sound wave needs air to travel. A light wave is an oscillation of electric and magnetic fields. A gravitational wave is a traveling oscillation of space-time itself. As it passes through a region, it does not push particles aside like water or air. Instead, it rhythmically stretches and squeezes the very space between them. Picture a perfectly circular ring of floating dust particles in empty space. As a gravitational wave passes through, perpendicular to the ring, a remarkable thing happens. The circle will first be stretched horizontally while being squeezed vertically, becoming an oval. Then, an instant later, it will be squeezed horizontally and stretched vertically, becoming an oval oriented in the opposite direction. This alternating distortion of space itself is the signature of a gravitational wave. It is as if the very ruler you would use to measure distance is being subtly and rhythmically warped. For decades, gravitational waves remained a theoretical curiosity. Even Einstein himself was uncertain if they were physically real or merely a mathematical artifact. The problem was their profound weakness. The distortion they cause is astronomically small. A typical gravitational wave from a distant cosmic event passing through Earth would change the length of a 1 kilometer-long ruler by a distance 1,000 times smaller than the diameter of a single proton. Detecting such a minuscule change was, for a long time, considered an impossible dream. That dream was realized on the 14th of September 2015, by the Laser Interferometer Gravitational Wave Observatory, or LIGO. The LIGO detectors are perhaps the most precise measuring instruments ever built. Each consists of two immense, 4-kilometer-long vacuum tunnels arranged in an L shape. A laser beam is split and sent down each arm, reflecting off exquisitely suspended mirrors at the ends, and then recombined. In perfectly calm space-time, the light waves returning from the two arms are tuned to cancel each other out, resulting in darkness at the photon detector. But when a gravitational wave passes through the Earth, it subtly changes the length of one arm relative to the other. One arm is momentarily lengthened while the other is compressed. This misalignment disrupts the perfect cancellation of the laser light, and a flicker of light is detected. The pattern of this flicker tells the entire story of the cosmic event that created the wave. The first signal ever detected, dubbed GW150914, was the sound of two black holes, each about 30 times the mass of our Sun, performing their final death spiral over 1 billion light-years away. For millions of years, they had circled each other, losing energy by emitting gravitational waves, and slowly, inexorably, moving closer. In the final fraction of a second, they whirled around each other at nearly the speed of light, and then merged into a single, more massive black hole. The event released more power in gravitational waves, for a brief moment, than all the stars in the observable universe combined. The signal LIGO captured was a direct recording of this last, frantic chirp, the rising frequency and amplitude as the black hole spiraled inward, culminating in the final ring down as the new, single black hole settled into a stable shape. For the first time, we did not see the cosmos. We heard it. We felt its vibrations. This discovery marked the beginning of a new era in astronomy, gravitational wave astronomy. We are no longer limited to observing the universe through light, from radio waves to gamma rays. We can now feel the subtle vibrations of space-time, allowing us to perceive events that are otherwise completely dark, hidden behind cosmic dust, or simply not producing any light at all, like the merger of two black holes. It is the ultimate confirmation that space-time is a dynamic, physical entity, a fabric that can be stirred, and whose vibrations we can, with immense effort and ingenuity, now record. We have learned to feel the tremors of the most powerful events in the universe, a silent symphony played on the strings of space-time itself. The most extreme prediction of general relativity, and the ultimate source of the most powerful gravitational waves, involves objects where gravity becomes so overwhelming that it warps space-time into a one-way street. Black holes. Black holes. We have followed the ripples in space-time to their source, the most violent events in the cosmos. But general relativity predicts the existence of objects so extreme, so dense, that they warp space-time into a configuration from which not even light can escape. These are the most enigmatic predictions of Einstein's theory, black holes. As you rest in the quiet darkness, let us explore these cosmic marvels, where the laws of physics as we know them are pushed to their absolute limit. A black hole is not a celestial body in the traditional sense, like a planet or a star. It is, instead, a region of space-time, a hole in the fabric of the universe, defined by its gravity. Its existence is the ultimate consequence of gravity's relentless one-way pull. Imagine a star many times more massive than our Sun. For millions of years, the outward pressure from nuclear fusion in its core balances the inward crush of its own gravity. But when such a massive star exhausts its nuclear fuel, this balance catastrophically fails. The core collapses, and if the remaining mass is sufficient, no known force in the universe can stop the implosion. The matter is compressed into an infinitesimally small point, and in doing so, it warps the surrounding space-time into a profound, bottomless pit. The boundary of this pit, the point of no return, is known as the event horizon. This is not a physical surface like the crust of a planet. It is a mathematical boundary, a one-way membrane in space-time. Think of it as a cosmic waterfall. If you are upstream of the waterfall, you can still paddle to safety, fighting against the current. But once you cross the edge, the current becomes irresistible. No amount of effort can carry you back upstream. The event horizon is that edge. Anything that crosses it, matter, light, information, is forever lost to our observable universe, its world line inevitably dragged inward. To an outside observer, an object falling toward a black hole would appear to slow down, its image becoming redder and dimmer due to extreme gravitational time dilation until it seems to freeze, fade, and vanish at the event horizon. The object itself, however, would cross this boundary and continue its journey inward. What lies at the very center of a black hole? According to the equations of general relativity, all the collapsed mass is compressed into a point of infinite density, a place where the curvature of spacetime becomes infinite. This is the singularity. Here, the very concepts of space and time, as we define them, cease to have any meaning. The laws of physics break down. It is a realm where our current understanding ends, a domain that likely requires a theory of quantum gravity to properly describe. The singularity is the ultimate destination for anything that falls within the event horizon, the final point where matter is crushed out of existence. The concept of such an object was so radical that even Einstein was skeptical it could exist in nature. The first mathematical solution describing a black hole was found by Carl Schwarzschild in 1916, merely months after Einstein published his final theory. While serving on the Russian front in World War I, Schwarzschild discovered a vacuum solution to Einstein's field equations for a spherical, non-rotating mass. His solution contained the description of the event horizon, a boundary now named the Schwarzschild radius in his honor. It would take decades for physicists like Subrahmanyan Chandrasekhar, Robert Oppenheimer, and John Wheeler to fully develop the theory, with Wheeler famously coining the evocative term black hole in 1967. For a long time, black holes remained theoretical curiosities, but today we have overwhelming evidence of their existence. We observe stars orbiting incredibly fast around an invisible dark companion at the center of our own galaxy, an object with a mass of 4 million suns, but with no visible emission. This can only be a supermassive black hole. We have detected the gravitational waves from the merger of smaller black holes. And in 2019, the Event Horizon Telescope collaboration presented humanity with the first ever direct image of a black hole's shadow. The image showed a bright, fiery ring of superheated gas swirling around the supermassive black hole at the center of the galaxy M87, with a dark central region, the shadow of the event horizon itself, silhouetted against the glowing background. It was a stunning visual confirmation of a century-old prediction, a picture of gravity itself. It is important to remember that black holes are not cosmic vacuum cleaners, randomly sucking in everything around them. At a distance, their gravity operates like that of any other mass. You could, in principle, orbit a black hole just as Earth orbits the Sunday. It is only when you venture extremely close, when you cross the event horizon, that the unique and terrifying nature of the black hole becomes inescapable. The tidal forces, the difference in gravity between your head and your feet, would stretch you into a long, thin stream of atoms in a process picturesquely known as spaghettification. A black hole is a testament to the raw, geometric power of gravity, a place where space-time is so warped that it folds over on itself, creating a one-way path to a destination beyond our current comprehension. Black holes represent the ultimate end of stellar life cycles, but general relativity also describes the origin and evolution of the entire universe. Applying his equations to the cosmos as a whole, Einstein discovered something he initially resisted, that the universe is not static, but dynamic and expanding. The expanding universe and the Big Bang. We have journeyed to the most extreme regions of spacetime, to black holes where gravity triumphs over all. But now, let us pull back our perspective to the grandest scale imaginable, the universe as a whole. As you rest, consider that the very space in which you are contained, the stage upon which all cosmic drama plays out, is itself dynamic and evolving. The application of general relativity to the cosmos revealed a truth that shattered the ancient idea of a static, eternal cosmos. The universe is expanding. This single, monumental discovery is the foundation of our modern understanding of cosmology, and it points back to a singular origin, an event of unimaginable density and temperature from which all things emerged, the Big Bang. The story of this discovery begins with Einstein himself. In 1917, when he applied his new equations of general relativity to the universe at large, he made a shocking discovery. The equations insisted that the universe could not be static. It must either be expanding or contracting. This was deeply unsettling to the scientific consensus of the day, which held the universe to be eternal and unchanging in its large-scale structure. To force his equations into alignment with this prevailing view, Einstein introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This constant represented a repulsive force that would precisely counterbalance the attractive force of gravity on cosmic scales, allowing for a static, stable universe. He would later call this the biggest blunder of his career. Meanwhile, other scientists were exploring the implications of Einstein's equations without such a preconceived notion. The Russian physicist Alexander Friedmann and, later, the Belgian priest and astronomer Georges Lemaitre independently found solutions to the equations that described a dynamic universe, one that was either expanding or contracting. Lemaitre took this a step further, proposing that if the universe is expanding now, then rewinding the cosmic film reel would mean that everything we see must have been much closer together in the past. He theorized that the universe began in a state of immense density, a primeval atom, or cosmic egg, which erupted in a colossal explosion, initiating the expansion we observe today. The observational evidence for this radical idea came from the American astronomer Edwin Hubble. Working with the powerful Hooker telescope at Mount Wilson in the 1920 seconds, Hubble was studying faint, fuzzy patches of light, then known as nebulae. He discovered that many of these were not clouds within our own Milky Way galaxy, but were entire island universes, galaxies in their own right. Vast collections of billions of stars located at staggering distances from us. By measuring the redshift of the light from these galaxies, Hubble made an even more profound discovery. With the exception of our nearest neighbors, the light from almost every galaxy was shifted toward the red end of the spectrum. This redshift was not the gravitational redshift we discussed earlier, but a Doppler-like effect, indicating that these galaxies were all moving away from us. And the most startling part was this: the farther away a galaxy was, the faster it was receding. This is the key observation. It is not that we are at the center of some cosmic explosion, with everything flying away from us. Rather, it is the space between the galaxies that is itself stretching. The classic analogy is a loaf of raisin bread rising in the oven. As the dough expands, every raisin moves away from every other raisin. A raisin that was initially twice as far away from you as another will find that the dough between it and you has stretched twice as much, so it appears to recede at twice the speed. This is Hubble's law, and it is exactly what we observe. The entire fabric of the cosmos, the space-time continuum itself, is undergoing a continuous and accelerating stretch. If the universe is expanding now, then the logical conclusion of running the clock backward is that everything was once compressed into an incredibly hot, dense state. This is the Big Bang theory. It is not an explosion in space, but an explosion of space itself, the rapid expansion of space-time from a primordial state of near-infinite density and temperature. From that initial, searing moment, space expanded and cooled, allowing energy to condense into the first subatomic particles, then simple atoms, and eventually, over billions of years, into galaxies, stars, planets, and us. The evidence for this is overwhelming and comes from multiple, independent sources. The first is the expansion itself, Hubble's observed redshift. The second is the cosmic abundance of light elements, particularly hydrogen and helium, which were forged in the first few minutes of the universe, in proportions that match Big Bang predictions perfectly. But the most definitive evidence came in 1965, with the accidental discovery of the cosmic microwave background radiation. This is a faint, cool glow of microwave radiation that permeates all of space, the afterglow of the Big Bang. When the universe was about 380,000 years old, it had cooled enough for protons and electrons to combine into neutral atoms. At that moment, the universe became transparent, and the light that was previously trapped was suddenly set free. That light has been traveling ever since, stretched by the expanding universe from visible heat into the microwave part of the spectrum. It is the oldest light we can see, a fossil imprint on the sky from the infancy of the cosmos, and its discovery was the final piece of evidence that cemented the Big Bang as the central paradigm of modern cosmology. The discovery of the expanding universe answered one profound question about our origins, but it immediately raised another, even deeper one. If gravity is an attractive force, pulling everything together, then the expansion of the universe should be slowing down over time. But is it? The ultimate fate of the cosmos depends on the answer, and it led to the discovery of the greatest mystery in modern physics: dark energy. Dark energy and the fate of the cosmos. Our cosmic journey has brought us from the smallest warps in space-time to the grandest of all scales: the evolution of the entire universe. We have seen how the discovery of the expansion of the cosmos answered the question of our origins, pointing back to the Big Bang. But as you rest in the quiet of the night, we now confront a discovery so unexpected and so profound that it has become the central mystery of modern cosmology. It is a mystery that dictates the ultimate fate of everything, and its name is dark energy. This is the story of how we learn that the universe is not only expanding, but that its expansion is accelerating, a finding that defies our basic understanding of gravity itself. For most of the 20th century, following Hubble's monumental discovery, cosmologists were consumed with one great question: what is the ultimate fate of the universe? Given that gravity is an attractive force, pulling everything together, the cosmic expansion must be slowing down. The key question was, by how much? Would the gravitational pull of all the matter in the universe be strong enough to eventually halt the expansion and pull everything back together in a big crunch? Or was the universe's initial momentum sufficient to allow it to expand forever, albeit at an ever-slowing rate, leading to a gradual cooling and fading in a heat death? The entire fate of reality seemed to hinge on this cosmic tug-of-war between the outward thrust of the Big Bang and the inward pull of gravity. It was to measure this rate of cosmic breaking that two independent teams of astronomers in the late 1992 began observing a special kind of stellar explosion known as a Type Ia supernova. These explosions are crucial because they are standard candles. They have a known intrinsic brightness. By measuring how bright they appear from Earth, astronomers can calculate their precise distance. Furthermore, by analyzing the redshift of their light, they can determine how much the universe has expanded since the moment the supernova's light was emitted. By comparing these two pieces of information for supernovae at different distances, and therefore looking back in time, the teams hope to plot the history of the universe's deceleration. The results, announced in 1998, were not just surprising, they were shocking. The distant supernovae, the ones whose light had been traveling to us for billions of years, were fainter than expected. This meant they were farther away than they should have been if the universe had been expanding at a steady or slowing rate. The only possible explanation was that the expansion of the universe was not slowing down at all. In fact, it was speeding up. Some mysterious repulsive force was working against gravity, pushing galaxies apart from one another at an ever-increasing rate. It was as if you tossed a ball into the air, and instead of falling back down, it shot away from you faster and faster, defying gravity. This discovery earned the leaders of the two teams the 2011 Nobel Prize in Physics, and sent a tremor through the foundations of cosmology. This mysterious agent of cosmic acceleration was dubbed dark energy. The name itself is a confession of our ignorance. It is dark because it does not emit or interact with light. and energy because it seems to be a property of space itself that drives this repulsive gravity. The most straightforward, though perhaps the most puzzling, explanation for dark energy is the revival of Einstein's old fudge factor, the cosmological constant. You will recall that Einstein introduced this term, represented by the Greek letter lambda, to force his equations to describe a static universe. After Hubble discovered the expansion, Einstein discarded it. But now, it was back. In this modern context, the cosmological constant represents a constant energy density inherent to the vacuum of space itself. As the universe expands and more space comes into existence, more of this repulsive energy appears, causing the expansion to accelerate. The physics of why the vacuum should have this energy and why it should have the specific, tiny value we observe remains one of the deepest unsolved problems in theoretical physics. The implications of dark energy for the ultimate fate of the cosmos are staggering. If the acceleration continues unabated, as a true cosmological constant would suggest, then the universe is headed for what cosmologists call a big freeze, or, more dramatically, a heat death. In this scenario, the expansion becomes so rapid that the observable universe beyond our local gravitational bound, our galaxy and its nearest neighbors, will effectively disappear from view. Distant galaxies will redshift into invisibility. The cosmos will become a vast, expanding, and ever colder emptiness, with isolated islands of stars eventually burning out in an immense dark void. An even more extreme version is the Big Rip, where a particularly potent form of dark energy could eventually overcome all forces, tearing apart galaxies, then solar systems, then planets, and finally atoms themselves, shredding the very fabric of space-time. Today, measurements from the cosmic microwave background, supernovae, and other probes tell us that dark energy constitutes about 68% of the total mass energy content of the universe. Ordinary matter, the stuff of stars, planets, and us, makes up less than 5%. The rest is another mysterious component, known as dark matter. This means that the universe we see, the universe of light and atoms, is just a tiny fraction of reality. The rest is a cosmos dominated by invisible, unknown entities, dark matter, which holds galaxies together, and dark energy, which is tearing the cosmos apart on the largest scales. We are living in a universe whose ultimate destiny is being shaped by forces we can only infer, not directly see, a profound and humbling realization. We have traveled from the stable universe of Newton to the dynamic, expanding, and accelerating cosmos of Einstein. We have seen how our understanding of space, time, and gravity has been utterly transformed. Let us conclude our journey by synthesizing all we have learned and reflecting on the magnificent legacy of relativity. Synthesis and conclusion, the legacy of relativity. And so, we have reached the end of our journey. As you rest in a state of deep tranquility, let us gather the threads of understanding we have spun over these lessons and weave them into a final, coherent tapestry. We have traveled a great distance, from the solid, predictable world of Newton to the dynamic, flexible, and deeply interconnected cosmos of Einstein. The legacy of relativity is not merely a collection of fascinating facts or bizarre phenomena. It is a fundamental shift in our perception of reality itself. It is a new way of seeing, and as we conclude, let us reflect on the landscape we have traversed and the profound truths it has revealed. We began our journey in the comfortable confines of classical physics, with its absolute space and universal time. It was a world of certainty, where the universe was a grand, predictable machine. But this comfort was disrupted by a crisis, the null result of the Michelson-Morley experiment, which hinted that light did not play by the old rules. From this crisis, Einstein built a new foundation with two deceptively simple postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light is constant for everyone. These two principles, so straightforward in statement, forced us to dismantle our most basic assumptions. They led us directly to the relativity of simultaneity, showing us that there is no universal now. Your present moment and mine are not the same if we are in relative motion. This was the first crack in the edifice of absolute time. From there, the consequences unfolded with an irresistible logic. The constant speed of light, combined with relative motion, demanded that time itself must be flexible, leading us to time dilation, where moving clocks tick slower. And in a beautiful symmetry, space itself had to yield, resulting in length contraction, where moving objects are measured to be shorter. We learned that these are not illusions, but real, measurable effects, confirmed in particle accelerators and essential for the accuracy of the GPS technology we use every day. These discoveries forced us to abandon the idea of space and time as separate entities and to embrace their unification into a single, four-dimensional continuum, space-time. Your life is not just a path through space, but a world line through this fused reality, a unique story written in the geometry of the universe. But Einstein was not finished. He sought to include gravity in this new picture, and his happiest thought, the Equivalence Principle, provided the key. By realizing that the effects of acceleration are indistinguishable from the effects of gravity, he was led to his masterstroke. Gravity is not a force, but the geometry of spacetime itself. Mass and energy tell spacetime how to curve, and the curvature of spacetime tells objects how to move. This single idea, of gravity as geometry, resolved the ancient anomaly of Mercury's orbit, predicted the bending of starlight, and redefined our understanding of the cosmos. It allowed us to predict the existence of gravitational waves, ripples in the fabric of spacetime, which we have now learned to feel with instruments like LIGO, listening to the collisions of black holes a billion light-years away. This geometric understanding of gravity opened our eyes to the grandest scales of all. We discovered that spacetime is not static, it is dynamic and expanding. The entire universe is growing, with galaxies carried along like raisins in a rising loaf of bread, a discovery that points back to a singular beginning in the hot, dense state of the Big Bang. And most mysteriously, we found that this expansion is not slowing down due to gravity, but accelerating, driven by a mysterious agent we call dark energy. This revealed that the universe we see, the stars, planets, and galaxies, constitutes less than 5% of reality. The rest is a cosmos dominated by dark matter and dark energy, a profound and humbling reminder of how much we have yet to learn. So, what is the legacy of relativity? It is the realization that the laws of the universe are not written in the simple language of forces acting on a fixed stage. They are written in the complex, beautiful language of geometry. The stage itself is the actor. Space and time are malleable, relative, and personal. Gravity is the shape of the cosmic stage. The universe had a beginning, it is evolving, and its ultimate fate is governed by energies we are only beginning to fathom. From ensuring your phone can navigate to allowing us to hear the echoes of black holes merging, relativity is not an abstract theory. It is the operating manual for our reality. As you drift into sleep, let this new understanding settle deep within you. The world is not what it seems on the surface. The forces that bind you to your bed, the light from the stars, the very flow of time you experience, are all part of a magnificent, interconnected, and dynamic whole. You are not just in the universe. The universe, with all its strange and wonderful rules, is in you. You have glimpsed the fundamental workings of the cosmos, the hidden geometry beneath the surface of reality. Rest now with this knowledge. Let your mind integrate these truths. You have completed a comprehensive journey through one of humanity's greatest intellectual achievements. Sleep well.